Assalamualaikum and greetings to all. Thank you, organizer, for allowing me to present my research. As stated here, I will present my research title, Analysis of Security Vulnerabilities in LoRaWAN Smart City. This presentation will highlight 5 components which are Introduction, Literature Review, Methodology, Results, and Conclusion. This research aims to evaluate the performance of the LoRaWAN protocol under jamming attack in smart city IoT networks connected using LoRaWAN technology. In this research, NS3 network simulation software has been used as a simulation tool. The study starts with designing a model of a smart city network. Following that, jamming attacks were conducted at the physical and MIC layer of the developed model. The effect of the jamming attacks on the communication performance was later analyzed. Performance metrics used in this research are packet loss rate and observing the effect of the packets that successfully pass through the gateway. The results significantly affect the packet loss rate as the number of jammers increases. To achieve the goal, three objectives must be performed, which is secondly, to implement a jamming attack at the physical and MAC layer of the designed model. And lastly, to analyze the effect of jamming attacks on the communication performance. Besides that, several research questions can be found while doing this topic, such as what will happen if jamming occurs in mobile mobility? And secondly, is there a difference if jamming is in mobile state compared to stationary? Third, are there differences in jamming effects in different models and environments? And lastly, what is the effect of jamming contained in the packet? Smart cities depend on connectivity. A higher spreading factor allows a higher packet success rate and time on a packet. LoRa network can scale well, achieving packet success rates above 95% in the presence of several end devices. Physical barrier can cause wireless network to drop. Next is the overview of how the jamming attack will be one of the security threats chosen in this study. It will happen in the network performance that will decrease as the number of jammers increases due to the probability of collision increasing, and the packet size will impact message airtime. Reducing the size of this message could allow message to beat the jammer's reaction time. The jamming requirement does not follow the regulated parameters of the corresponding subband, such as duty cycle, packet length, and transmit power. This LoRa time on air is the LoRaWAN equation for time on air. The following equation is used to calculate the duration of a symbol using a spreading factor, where PL denotes the number of payload bytes, H represents the presence of header, DE means the presence of cyclic redundancy check, and CR is the coding rate at which coding occurs. The total preamble and payload durations determine the time required to transmit the packet. There are 3 plans on how to do this research. The first is to design and model a smart city network in the NS3 simulation tool by defining the suitable parameter, and then simulate the network to obtain expected results. The relationship between packet loss rate with the number of jammers was analyzed, and the effect of packet received by gateway using the Wireshark network has been analyzed also. In this NS3 model part, most models use the default NS3 LoRaWAN model. Some jamming models, such as jamming application, must be added manually in this model simulation. Adding this application allows jamming device to transmit and interrupt the transmission. In this research, the time allocated to the transmission is the same as the regular end device. Jammer LoRaWAN MAC need to add jammer in the MAC layer. This model will change the maximum payload value from the original payload amount. It also ensures the channel and spreading factor for jamming transmission. Simple jamming LoRaWAN physical is created to make some modification by adding this kind of trait in the simple and device LoRa physical model. In environment 1, all the end devices are fixed with a line of sight environment. The closer each node is to the gateway, the smaller the spread factor and the higher the data rates. Each of the end device nodes has a different spreading factor. Even though urban is dedicated to 5 km, the spreading factor does not reach until 12 in this simulation. So extending more distance assumes that all the spreading factors can be achieved when designing the model. The jamming will only occur in spreading factor with the same bandwidth. As for environment 2, observe the condition and effect of jamming when the end devices are in mobile condition. In this model, two gateways are used since the devices are moving. Some device might be out of range when transmission occur because the model is in rectangle but the radius is in circle. So two gateways are used to cover this model range. When the end devices are in mobile condition, spreading factor 12 is the most suitable for long distance since it will moving randomly. Environment 3 modeling is almost same as environment 2. In this environment, it is observing the effect of jamming in mobile situations. This model is designed when end device and jamming device are in mobile condition, while in environment 2, jamming device are in fixed position. Environment 4 observe the packet when the model is in indoor and non-live on-site condition. This case will also observe the packet and might be compared with environment 1 in packet loss before and after the jamming attack. The building parameter is automatically calculated through the NSC program simulation corresponding to a given radius. In this time on air table, show the maximum payload parameter. The parameter of data rates and maximum payload is based on AS923 MHz. Semtech has regulated the parameters of data rates and maximum payload based on the LoRa frequency used in Asia and Malaysia. The data rate determines the maximum application payload specified. All these parameters are implemented in the physical and MAC layer of the LoRaWAN network. The data rate determines the maximum application payload specified. If a node can operate in the worst case scenario, the worst data rate spreading factor 12 should be used, with the node sending no more than 51 bytes. In this study, we use payload 50 since it will be the maximum payload since mainly spreading factor used in this study is 12. And for the jamming attackers, we will use a massive payload that exceeds the maximum payload number to disturb the transmission. As for packet loss rate versus the number of jamming, we can see that when the number of jamming increases, the number of packet loss will increase also. All environments will face the same consequence. When more jamming devices are deployed, it will cause more collision and disruption with the end devices. In environment 2, we can observe that when the number of end devices increase to 300, the number of packet drops without disturbance from the jamming attack. It happens because during the transmission packet, some device might not be within the radius of the network area. After all, they are moving randomly. The observation also shows that the number of packet loss is higher than in environment 1. When 40 jammers were added, almost none of the packet was transmitted. It might happen because only spreading factor 12 is used for both devices in this environment. In environment 3, these results are intended to compare jamming device in the mobile state. It needs to be determined whether different methods will produce statistically significant results. However, packet loss rate between the two environments do not differ much. This may be because the jamming packet that initially wanted to make a mess of the end device is suddenly outside the network radius. So the intention to make a mess was to step back because the jamming device was not in the same network radius. For environment 4, the difference is adding the building. This model needs to observe the difference between the line of sight and non-line of situation. Before jamming, the packet loss difference between environments 1 and 4, which is a fixed condition, is slightly different. It has more packet loss than in environment 1 because physical obstacles can cause wireless networks to drop packets. Note that there is blank in this table showing that during the packet transmission, some of the packets happen because the cumulative packet received is not found in the tracker. This will discuss more in the following slide. For this part, let's compare all environments with environment 1. Environment 2 and 3, it has much different packet loss, although without the interruption of jamming because it is in moving condition. It may be that during the packet transmission, the device might be out of radius range during the transmission process. While in environment 4, since we are not building in the simulation, the disruption of obstacle may cause the packet penetration drop. When a jamming attack occurs, all environments cause significant packet loss, especially when 40 jammers are added. A difference in packet loss can be seen clearly, ranging from 0 to 40 jammers. The environment experiences the worst situation when the end device is mobile. Based on the graph, there are slight difference in the packet loss rate between environment 2 and 3. The packet loss between the line of sight in environment 1 and the non-line of sight in environment 4 conditions show a minor difference. In the presence of a jamming attack, when 40 jammers are added, the packet loss for environment 4 increases and half is lost more than environment 1. Based on the results observed in the Wireshark network analyzer, the condition for a signal-to-noise ratio before and after jamming was verified. Before a jamming attack has been implemented, all packets obtain 10 dB signal-to-noise ratio, especially in environment 1. After the jamming attacks, the SNR for the surviving packet is unstable. This analysis from the Wireshark analyzer is obtained from environment 4 with 100 device and 20 jammers. Based on the graph notice that in the previous slide results, some packet loss rates between the number of jammers are not specified due to the packet not be found in the tracker. When the transmission occurs, there is an error in the packet received at the gateway, causing the packet to be not found in the tracker. If the gateway can detect some jamming packets during the transmissions, the gateway immediately abort the simulation. The gateway terminates the transmission because it detects a mismatched frame payload due to the jamming interference. Furthermore, each legitimate end device has its device address, which allows it to be recognized from each other through ODA activation to produce an application ID and an application key, as well as a device ID to generate the network session key, application session key, and device address. In contrast, jamming devices do not have any device address. As for the conclusion from the explanation results before this, the results are in line with the previous researches, which is that the packet loss will increase depending on the increasing of number of jammers. Different smart city models and environment will give different packet loss in jamming impact. Some areas need to be emphasized and significantly impact the presence of jamming. Several effects such as unstable signal-to-noise ratio can also occur and cause the packet to be corrupted. Packet loss other than jamming can also be due to the problem of physical errors, as stated in the previous literature review part. To further develop this research in the future, some of the future recommendations can be implemented to extend this study. The impact of the different power transmissions, frequency, and duty cycles must be verified in future work. A low-level technique can be used to reduce the jamming performance. It is possible to use an intrusion detection system to mitigate and avoid jamming attacks, and include cryptographic primitives to maintain the integrity of packets and drop the packets. Another mitigation method that can be implemented in this research is deploying artificial intelligence algorithm integrated into IoT device to make them handle radio interference.